From the dawn of civilization, humans have been intrigued by the Earth's rocky framework. Early naturalists observed patterns in rock formations. They recognized layers, fractures, and folds. These pioneers meticulously recorded their observations. They sketched intricate maps and diagrams. These early efforts marked the genesis of geological mapping. This endeavor laid the groundwork for the systematic study of Earth's structure. Early geologists faced the daunting task of deciphering a complex, often cryptic, geological language. To truly understand the evolution of structural geology, we must first grasp the language used to describe the Earth's deformed crust. Imagine a rock, once a formless mass, subjected to immense pressure and heat deep within the Earth. This process, known as metamorphism, can fundamentally alter the rock's structure, giving rise to distinct features that geologists use to unravel its history. One such feature is foliation, a general term for any repetitive layering in metamorphic rocks. This layering can manifest in various forms, each with its own specific name and characteristics. For instance, schistosity describes closely spaced planar surfaces along which the rock breaks easily. Picture a stack of playing cards. The ease with which they separate along their flat surfaces is analogous to schistosity in rocks. Another important term is cleavage, which refers to the tendency of a rock to split along parallel, closely spaced planes. Unlike schistosity, cleavage can develop in both metamorphic and sedimentary rocks. Imagine splitting a piece of slate used for roofing tiles. The clean, flat surfaces result from the rock's well-developed cleavage. Understanding these terms is not merely an exercise in memorization. Each term represents a specific process that the rock has undergone. By identifying and analyzing these features, geologists can reconstruct the history of deformation and metamorphism that a rock has experienced. The origin of schistosity, a defining characteristic of many metamorphic rocks, puzzled early geologists. They observed this pronounced layering in rocks like schist and gneiss. However, the mechanisms responsible for its formation remained elusive. Some proposed that schistosity resulted from the recrystallization of minerals under pressure. They argued that the alignment of mineral grains perpendicular to the direction of stress created the observed layering. Others theorized that schistosity developed through the rotation of pre-existing mineral grains. They envisioned the grains aligning themselves like tiny compasses, pointing towards a magnetic field, but in this case, influenced by the direction of pressure. These differing viewpoints fueled vigorous debate within the geological community. The search for the true origin of schistosity drove further research and observation. The resolution of this debate would have profound implications for understanding mountain building. Schistosity and other forms of foliation are often found in mountain ranges. Deciphering their formation was key to unraveling the processes that uplift these colossal landforms. The quest to understand schistosity pushed geologists to delve deeper into the microscopic world of rocks. Enter Bruno Sander, an Austrian geologist who revolutionized the field of structural geology in the early 20th century. Sander's groundbreaking work focused on the microscopic analysis of deformed rocks. He meticulously studied the orientation and shape of mineral grains in metamorphic rocks. His observations led him to develop the concept of fabric in rocks. This referred to the spatial arrangement and orientation of mineral grains and other features within a rock. Sander recognized that the fabric of a rock could provide invaluable clues about its deformational history. He argued that the shape and orientation of mineral grains were not random. Instead, they recorded the directions and magnitudes of stresses that the rock had experienced. Sander's work laid the foundation for the field of structural petrology. This field examines the interplay between microscopic rock fabric and large-scale geological structures. Sander's influence extended beyond his own research. He established the Austrian School of Structural Geology, a group of geologists who shared his passion for detailed microscopic analysis. The Austrian school made significant contributions to the understanding of rock deformation. They developed new techniques for analyzing rock fabrics and interpreting their significance. Their work had a profound impact on the study of mountain building, faulting, and other tectonic processes. Section 5. Symmetry in stone, unlocking the secrets of deformed rocks. Imagine a perfectly symmetrical butterfly, its wings mirroring each other with astonishing precision. Now, envision the same principle applied to rocks. those seemingly chaotic masses of minerals. Surprisingly, symmetry plays a crucial role in understanding deformed rocks, offering a powerful tool to decipher their complex histories. In the world of structural geology, symmetry is not just about aesthetics. It's about recognizing patterns in the arrangement of rock features. These patterns, often subtle and concealed within the rock's fabric, hold the key to unraveling the forces that shape them. Just as a detective analyzes fingerprints to reconstruct a crime scene, structural geologists use symmetry elements to reconstruct the history of rock deformation. Consider a simple fold in rock layers. The way the layers are mirrored on either side of the fold axis reflects the symmetry of the deformation. By analyzing this symmetry, geologists can determine the direction from which the compressive forces originated. This principle extends to more complex structures, allowing us to unravel the intricate dance of tectonic plates over millions of years. Section 6. A golden age of discovery, advancements in structural geology, from 1911 to 1939. The period between 1911 and the outbreak of World War II witnessed a flourishing of research in structural geology. This era saw a surge in field study. Geologists ventured into remote and challenging terrains, armed with compasses, hammers, and a thirst for knowledge. They meticulously mapped vast areas, documenting folds, faults, and other structural features. Simultaneously, advancements in microscopy revolutionized the study of rocks at the grain scale. Geologists could now peer into the heart of deformed rocks. They observed the intricate arrangements of mineral grains, revealing the subtle clues of past tectonic events. This period saw the development of key concepts like strain analysis. This allowed geologists to quantify the amount of deformation rocks experienced. The integration of field observations with microscopic analysis marked a turning point in structural geology. Geologists began to connect the dots between the macroscopic and microscopic worlds. They realized that the grand structures they observed in the field were ultimately the product of processes happening at the scale of individual mineral grains. Section 7. Mountains unfolded, the Swiss and Highland schools' contributions. The towering Alps, with their majestic peaks and intricate folds, have long captivated the human imagination. It's no surprise that these mountains became a natural laboratory for pioneering work in structural geology. The Swiss School of Geology, led by luminaries like Albert Heim and Emil Argand, made groundbreaking contributions to our understanding of mountain building. The Swiss geologists meticulously mapped the complex nappe structures of the Alps. These vast, overturned folds testified to the immense forces involved in mountain building. They developed new techniques for unraveling the sequence of events that led to the formation of these complex structures. Their work laid the foundation for modern interpretations of orogenic belts, the collision zones where continents collide. Across the English Channel, the Highland School of Geology, led by figures like Archibald Geikie and Charles Lapworth, made significant contributions to the study of faulting and thrusting. Working in the Scottish Highlands, they unraveled the complexities of thrust faults, low-angle fractures along which rocks are pushed over each other. Their work provided crucial insights into the mechanics of mountain building and the development of fold and thrust belts. Section 8. The experimental frontier, simulating Earth's forces. While field observations and microscopic analysis provided invaluable insights into Earth's structure, geologists faced a fundamental challenge. They could observe the aftermath of tectonic forces, but they couldn't directly witness these forces in action. This limitation led to the emergence of experimental structural geology in the mid-20th century. Pioneering researchers in the United States, equipped with new technologies and a spirit of innovation, began to simulate the Earth's powerful forces in the laboratory. They subjected scaled-down models of rock layers to controlled stresses and temperatures. These experiments allowed them to observe how rocks deform under various conditions. They could study the formation of folds, faults, and fabrics in real time. The results of these experiments revolutionized our understanding of rock deformation. They provided quantitative data to support theoretical models. They also revealed unexpected behaviors, challenging existing assumptions and leading to the development of new theories. Experimental structural geology became an integral part of the field, bridging the gap between observation and theory. Section 9, a unified vision, fieldwork and microscopy in modern geology. Today, structural geology stands as a vibrant and multifaceted discipline, drawing on a rich legacy of fieldwork, microscopic analysis, and experimental techniques. Modern structural geologists embrace an integrated approach. They venture into the field equipped with GPS units, digital mapping tools, and a keen eye for detail. They collect rock samples, bringing them back to the laboratory for analysis. Using sophisticated microscopes and analytical techniques, they delve into the microscopic realm of rocks. They examine the intricate arrangements of mineral grains, unraveling the subtle clues encoded in their shapes and orientations. They use computer modeling to simulate rock deformation. This helps them understand how geological structures form and evolve over time. This integrated approach has led to a deeper understanding of Earth's dynamic processes. Structural geologists are at the forefront of research on mountain building, earthquake hazards, and the formation of natural resources. Their work has practical applications in fields like oil and gas exploration, mining, and civil engineering. Section 10. Conclusion: the ever-evolving story of Earth's architecture. The journey through the evolution of structural geology reveals a relentless pursuit of knowledge, driven by curiosity and a desire to comprehend the Earth's intricate workings. From the early pioneers who meticulously mapped rock formations to the modern scientists who simulate Earth's forces in the laboratory, each generation has added to our understanding of this dynamic planet. As we delve deeper into the Earth's structure, we uncover new mysteries and complexities. The story of structural geology is far from over. It's an ongoing narrative, continually being rewritten as new technologies emerge and new discoveries come to light. The quest to decipher Earth's rocky script continues, fueled by the same spirit of exploration that inspired the earliest geologists.